excited to present to you today our final design for the Amazon industrial site. Like I said, I'm the project manager and I'm also the transportation engineer for Hayman Engineering. With me today, I have Alex Ketter, our structural engineer, and Jack Larson, our environmental engineer. Giving a quick project overview, as a transportation engineer, I was in charge of designing a connecting road between County Road 17 and County Road 19. On this connecting road is a three-way intersection where it meets with an Indiana Toll Road entrance. This intersection is signalized, and where this toll road meets with, or where this extension meets with County Road 19 is a stop-controlled intersection. Additionally, part of my scope was to provide access to the structural building on site, as well as design for the parking lots for the academic building. The structural scope was to design the structural members for the academic building, including classrooms, offices, laboratories, and the auditorium. And the environmental part of our project was to design a water treatment facility that could treat 1 million gallons of water per day. Included in this design was the treatment train and distribution to the fire safety system on site. Beginning with the transportation portion of this project, my design was all in regards to the Indiana Design Manual, the AASHTO Green Book, the Elkhart County Regulations, and the Americans with Disability Act. So for the Indiana Design Manual, figure 46-2D controlled my intersection design. Our design vehicle was the WD-67. For a 90-degree turn, the turning radius is 125 feet. As you can see on the right side of the screen, figure 53-8 from the Indiana Design Manual controlled my horizontal and vertical alignment design. Moving into my cross-section, a typical cross-section for this project is a 2-lane road with 1 lane going in each direction. There's a 2% cross slope, which is considered a normal cross-section. I have a 6-foot paved shoulder and a 2-foot unpaved shoulder. The depth of this pavement was determined using structural number, and for this type of roadway, and for its considered use, a structural number between 3 and 4 was determined to be ideal, with an aggregate depth of 6 inches, a base asphalt depth of 3 inches, an intermediate asphalt depth of 2 inches, and a surface asphalt depth of 2 inches. We got a calculated structural number of 3.81, which is sufficient for this site. On our shoulders, a surface asphalt depth of 2 inches and an aggregate depth of 11 inches, which is determined to be sufficient for its use. And here is a typical cross-section with a center lane. The center lane would be used for turning movements, specifically left-hand turning movements. As you can see with my cross-sections, we also have a 20-foot clear zone, which is included with the shoulder and the ditch for slope. Additionally, I have ditches on either side, which would be used for any roadway drainage. I do not have a water resources member to my group, so any water resources work would be hired to another party by the owner. So just an overview of what my alignment looks like. Once again, the Indiana Toll Road would be slightly realigned to match my new design. So the intersection meets at a 90-degree angle, and then the parking lots would dip, and then the alignment would dip below the building. So the parking lots are to the north of the alignment. Zooming in on my intersection design, so the deceleration length was determined based off the design speed for this project, determined to be 385 feet for the 45-mile-per-hour design speed. And then once again, the radius for for both of these intersections is 125 feet. For the County Road 19 and County Road 4 intersection, which is a stop-controlled intersection, the County Road 4 extension would be stopping for County Road 19 traffic, as our scope did not specify any changes to County Road 19. Moving on to my west lot, the number of parking spaces for this lot is more than sufficient for the use of this building, but I wanted to design for a little bit of redundancy and potential growth for this school. So this parking lot has 68 parking spaces and 5 ADA spaces, 3 of them being van accessible. Additionally, with this parking lot, the stalls are separated from the moving traffic by curbs to provide safety for the pedestrians and other vehicles. So additionally, during drop-off and pickup times, there are buffered shoulders where parents can idle while waiting for pickup and drop-off for their children. On the south lot, it is mainly used for staff and bus traffic. It is designed to be one-way, similar to the other one, but these ones are angled at 45 degrees to ensure that there's only one-way traffic. These bus stalls will be utilized during the drop-off and pickup times. Once again, the stationary stalls are separated from the moving traffic by curb. Moving into my cost estimate, it was estimated using the NDOT unit price summary. My roadway cost, which includes the traffic equipment, pavement, striping, and cut and fill, was estimated to be $3.1 million. My parking lot, which would include both parking lots, which includes pavement, striping, and grading, came out to be $900,000, and with a 20% contingency, the total cost came out to be $4.9 million. I will now hand it over to our structural engineer.
Thank you, Leah. Just to go a quick little overview of what our floor plan actually looks like. We have our outdoor cover area, that's for the pickup and drop off, and inside we have our classrooms, labs, offices, and our auditorium, which is a double height auditorium. And all this was done in compliance with ASCE 7-16, steel manual, and international building codes. Moving on to these loads that we use, the snow load was the controlling load, especially when it came to the roof load. This was found with the ASCE hazard tool, and then brought down with different factors on geographically where it is, the importance factor, we're making a school building, or we're designing a school building, not a warehouse. The same thing happened with wind and seismic to count for those lateral loading, because we're in Indiana, we have to worry about the wind, not as much the seismic. And then those gravity loads, for the roof, we use a metal deck, and the reason it's 20 PSF as the dead load is to account for self-weight of some materials, such as for the future when we start designing for electrical, maybe piping, plumbing, anything that will be up in rafters, we accounted for that. And then the live load is 20.79 PSF, and that's the snow load from that calculation in the last slide. We use 22 PSF in our calculations to have a little bit of a contingency and to be a little more conservative. And then moving under that floor dead load, 50 PSF is our composite deck, and including the self-weight. And then the live load was the classrooms, offices, and labs and corridors. 80 PSF was the max that we needed to use, but for some area calculations, such as the classrooms, are less than 80 PSF. So those beams and columns and girders may have been a little smaller than the ones that needed to account for those corridors, which gave us the 80 PSF. Then moving on to the member selection, the reason I have this is most of them have changed ever since I put all the loads into RESA, so very different from the last presentation, but I'm not going to go too much in depth, but the beams, girders, and columns all changed. But the main thing I want to point out is that the interior for all of the girders and beams are larger than the exterior because they have to bear more load, and the same goes for those columns, but the new addition was the truss design for the auditorium. So the auditorium includes a truss design of 2 channels on the top and bottom, and then single angles, cross bracing, and vertical. I will have a visual of that later in the presentation to show you. And then there's beams, and then we used bracing for the auditorium because when we ran the calculations, that was the most unstable and the part that deflected the most due to all the loads applied. So when we added the bracing, that stopped all that. And then columns. This is an elevation layout looking north on the building from the side. This is just kind of that visual showing the gravity loads is distributed throughout the top and the middle floor, and it shows that each story is 15 feet tall, and the arrows just show that we account for the lateral loading just the way it would make the building shift. And then we have our structural layout. This is just showing all those columns, beams, and girders, And then the truss design, as I said, we will have a visual of that in a few slides, but this is more of that rendering of it. This is from RISA floor, so it doesn't have the truss design. The truss design will be in the next slide, but this just shows more of that visual, the outward covered area. The elevator is that red little marking just to show you where that is, and just all of the beams and columns and girders. There, sorry. This is that truss design. This covers that auditorium, which is a double height auditorium. The reason we wanted a truss is just to be able to distribute that load without having columns going up and down the middle, beams and girders, but in doing that, the smaller the truss is, it's not very large, but it spans over a long way, and we can prefabricate most of that off-site and bring it on-site, which makes the assembly a lot quicker and more cost-effective. And that goes also in the top left, we have our bracing that we used. Again, this was the area where it deflected the most because there wasn't as much support as the other parts of the building had. So when we added that bracing, all the calculations and RISA showed that the building was stable after adding those. Then moving on to our cost estimate, it goes a little more in depth in my report, but this is more of just an overview of building structure and materials, labor and construction cost, site conditions, and the whole design, and there's a 10% contingency. This came out to $7.4 million. And with that being said, I will pass it on to environmental.
Hello, as said, I am Jack Larson. I am the manager of the environmental scope of this project. To reiterate, as decided through phase one of this project, I went to design a groundwater treatment plant due to the abundance within the area. Beginning, I designed a groundwater pump, which would then filter into a rapid sand filtration system, in which we'll discuss that more in the presentation, followed by a disinfection basin, which will then be stored in a water storage filter. The plan is to distribute roughly around 1 million gallons of water per day to the surrounding area. We'll discuss more about that later in the presentation, where it is then distributed to the schoolhouse as well as to the fire safety system. These have been designed with codes from the Environmental Protection Agency, the World Health Organization, and guidelines from Elkhart County regarding water treatment and fire safety. Start off with the groundwater pump. There's going to be a total well pump of around 100 feet with a minimum pump capacity of 700 gallons per minute being pumped out of the ground. There will be 2 pumps on site, alternating usage, each designed for the same amount of gallon flow rates. Different from the first presentation, originally I had slow sand filtration activated carbon. However, through my own research and guidance from my advisor, it was decided that a rapid sand filter would be more efficient in the water treatment process. As shown here, it'll be a 10-foot height with about a 5-foot diameter. Going through, there will be three layers. There'll be 3 layers through it that will help to filter out any unwanted chemicals and suspended solids from the groundwater. The first layer of anthracite coal, 2 feet high, is going to filter out any of the suspended solids and turbidity within the water, followed by silica sand, which will absorb any of the finer particles that are left in the water. Finally, with a fine gravel layer, which is designed to be support for an even drainage into the collection basin. Where it is then transferred over to the disinfection basin with a contact time of about 30 minutes and a chlorine dose of roughly 5 milligrams per liter. It plans to filter out any of the harmful chemicals that could be underwater, as well as such as magnesium or calcium due to the hardness of Indiana water. There will be 3 tanks on site with 1 on standby. Finally, with the water storage system, there will be 2 tanks on site, each containing 750,000 gallons of water. The water will be made sure to be moved around to avoid staticness with the water tanks being alternated in their usage. Finally, something that was not previously discussed on, at least to this much depth in the previous report, was the fire safety system for the schoolhouse. It is designed to pump out 150 gallons per minute at a power 20 psi for a minimum of 2 hours. With the sites approximately 2,500 feet away from the schoolhouse, I designed a piping system created from ductile steel with a 12-inch diameter that will pump the water from the site to the school, as well as a T intersection piping that will go off to the side where it could be opened up with a gate valve, and it will be able to pump the water into the fire hydrant in case of an emergency. Now, on to the cost estimates. I'm looking at a $5.5 million cost. There is a 10% contingency factored into each of the facilities, which includes installation, testing, and designing, as well as the general outline of the plans. Building construction costs were not included in this estimate as that's outside of my scope. I will then pass it on to Leah, our question teacher.
Thank you. So with the structural, transportation, and environmental, and each individual contingency, our total project cost came out to $17.8 million. And with that, I'd like to thank you for your time today, and I'd like to open the floor to any questions. Yes.
Okay, start with Jack, I believe. Oh, I am limited on the number of questions.
Yeah, let's go 2 questions each, and then if there's time,
Okay.
we'll circle
So,
back.
Jack, I'll make it maybe 1 for you and 1 for Leah. So you mentioned that the filtration is to remove suspended solids, and you are using a groundwater. Where do these suspended solids come from?
From these, it would just be from testing. If there was still a high chance of any contaminants are in the water, so I just wanted to account for any possibilities that could have been from there.
Well, filters don't remove chemicals.
Yeah.
They remove suspended solids, but where they come from, usually through a pre-oxidation process. And so just to make sure that in there. And why do we need a separate tank for disinfection? This is water treatment, not wastewater treatment. So you can actually, since you have a storage facility, you can add your chlorine or whatever disinfectant into the storage tanks, correct?
Yes, it was for the sake of redundancy, just to make sure of any sort of, just making sure the water would be safe in case of any contaminants.
Okay, thank you. Leah, quick question. In the second parking lot layout, I saw there is sort of a large distance, if that drone is to scale, between the parking spaces in there. Can you go back to that drawing and tell me, because that's the objective of having those parking spaces at an angle, and I see sort of a huge space between the 2 rows in there. Why did you do that?
Originally, I had them just at 90 degrees in the center, which required that space. And then I already had the radiuses for the entrance and exit of that parking lot design, so I probably should have shortened that. I don't think that the space is as big as it looks.
So it's not to scale.
Yeah, well, it is to scale. It's just, with the entire design, it's probably about 40 feet between the two, so it should be closer to 24 feet.
Yeah, thank you.
Yes.
I have questions for Alex. Yeah, could you please go to the, yeah, so maybe pass this one, so number 15, please. Okay, so you showed us here that you have calculated snow load and wind load and seismic load and then compare them, and the wind load is controlling, regarding the lateral load.
Yeah.
But on the elevation, you didn't give us the values of this wind load. So,
Yes, those are in my report. I just had that on the elevation plan as a visual of showing you that I accounted for the lateral loading.
but you don't have the numbers now?
I don't know them right now, but I know they're in my report when I talk about wind
They are.
loads. Yeah.
Could you go to the calculation of the, yes, this one. Do you, when you say the floor dead load is 50 PSF,
Yes.
did you consider the self-weight of the material? Because you're mentioning that you have like 5 inches of concrete. 5 inches of concrete by itself, it comes up to close to 60 PSF.
Is that okay? Maybe
Yeah, even if you don't calculate the self-weight of the joist that you have used,
Mhm.
that's way below the. So did you consider anything that I cannot notice here?
Maybe not. That might have been an error on a typo typing it in. I'd have to check my calculations again.
And also for the live load of the classrooms, offices, labs, and corridors, all of them have the same?
No, I explained, I just wanted to show the highest live load. So I said like for the classroom is only 50 PSF, so when I made that area load into RESA, I made sure I used 50 for that and so forth for the offices and labs. Corridors were the only thing that really controlled, and the corridors are like the hallways, so we needed to account for that a lot in the structure itself, because it kind of roamed around the offices and labs, and that kind of controlled a lot of those beams, and you have to account for that also.
So could you move to the next slide, please? Maybe next, the one that shows I mentioned, you don't also put the numbers for the gravitational forces.
Yeah, again, this was just kind of a visual, just to show.
Oh, it's just in the.
Yeah.
Okay, so what are the lateral force resisting system? Because you have the wind load, right? So what is the lateral force resisting system in 2 directions?
In 2 directions, it was in the X and Z directions.
Yeah, what are the lateral force resisting system? What members or what system is going to resist the wind load?
When I ran my calculations, looking at like deflection, the biggest of movement was the truss, or not the truss, the auditorium area, which led me to putting bracing there to help from moving too much, I guess.
In one of the directions, like let's say for example, north-south maybe?
Yeah.
How about the other direction? What's the,
when I ran it in RESA, I guess that's all that came up
So
was
you-
in that direction, so.
and that one brace was enough because the wind load, seismic load, they are reversal, so that member should resist both compression and tension, right?
Yes,
So you check that and,
yes.
okay, thank you very much.
Yes.
2 quick questions. What is the clear zone?
The clear zone is the area off of the roadway that is clear of any obstructions in case of emergencies and vehicles need to go onto the shoulder.
Okay. And how did you get your company name?
I can't answer this one. I think it's got to be.
I don't know, they just kind of brought it up to me and I was like, oh, that sounds good.
Our former project manager, Barrett Church,
Yeah.
I think he was just looking towards towards the future, and the future project manager, Leah Hammond, often mispronounced as Leah Hayman. I think that's where it came from, yes.
So I had a question for the group.
Yes,
I was going to ask about your 20% contingency.
yes.
It seemed a little high at this point, but then the other members had 10% contingency. So how did you come up with your contingency and why are they different?
So contingencies for transportation, mine's a little bit higher because I have to take into account traffic control, and then the changing costs of materials. Using the NDOT unit price summary can only get you a ballpark estimation. The numbers for those materials vary widely, which is why I used a 20% contingency for any unforeseen costs.
And then,
And then for them, a 10% contingency was more than adequate for any unforeseen costs for their design.
thanks. We do have time for other questions. So here's your chance.
No, I don't want to.
Anybody? Okay, thank you.